Students, hello. Welcome to Lesson 79. I'm trying a new filming arrangement, and I'm hoping this will work out well for you, adjusting my light and such. Lesson 79 has two topics. The first topic is metric volumes, and we're going to do some conversions of metric volumes that show up commonly in physics and chemistry classes. And then we're also going to talk about a geometry topic, 45, 45, 90-degree triangles. Okay? Two very different topics that don't relate to each other much at all, but that's okay. That gives us variety. All right, let's go to metric volumes. Let me introduce to you a friend of mine. This is a bottle of Perrier water, and you'll notice, well, you probably can't see it, but right down here it says this is 1 liter. 1 liter of water. I want you to be able to visualize that, because what we're going to talk about is a measurement that is often used, that's Ranger barking, it's often used in physics and chemistry to describe volumes. So we're talking about volumes, that's why I wanted you to visualize it in this water, but there's a specific unit of metric volume that is literally about this size. Imagine the size of a sugar cube, and it is 1 centimeter cubed. And we call that, we have a special name for it because it's used so often. We call that 1 milliliter. I just want to make sure that I spell it right. This is not a milliliter, which is something else. It's a mill, 2 L's, I believe, milliliter, which means that 1,000 cubic centimeters equals 1 liter. Or another way of saying the very same thing is that 1 milliliter, 1,000, oops, my bad, 1,000 milliliters equals 1 liter. So these are some relationships that we're going to use in doing conversions that will be very useful. And what you'll see, well, no, I'm right, I'm not even going to tell you. Okay, so there's our little 1 centimeter, and it's also 1 centimeter on the back. It's like a sugar cube, more or less. All right, so let's look at example, say 79.1, and I'm on page 328. And in this example, we're being asked to use unit multipliers, misspelling, multipliers to convert 14,000. You guys, my eyes are really iffy right now. It's a day after my surgery, and I am really struggling to see properly, so hopefully I'll catch any mistakes that I make. We want to convert 1,000 milliliters, notice it's lowercase m, uppercase L, to liters. Okay, so it sounds like it's a volume problem. We notice that right away. We know that liters is a measurement of volume. Remember, think of this guy. It's a volume measurement. And we know that it's already measured in its milliliters, so we know that's code for our little tiny sugar cube. And so we're going to convert that number to liters. Oh, there's Perrier again. Okay, so we have 2 ratios that link milliliters to liters, and we're going to use this form of our conversion right there. So we know that for every 1,000 milliliters, we have 1 liter, and we also know that for every 1 liter, we have 1 milliliter, okay? So we're planning our conversion here. We're starting with 14,000 milliliters, and we want to end up with liters. So the first question we ask ourselves is, which of these ratios do we want to use? We want to use the one, I'll remind you of the rule, we want to use either the starting unit on the bottom, or, oh, I did this wrong. My bad. Hope you guys saw that and were like, what is she doing? It's a very useful part of class that I miss when I'm doing these videos, is I don't have you guys to catch my dumb mistakes, so I miss you. Okay, so we want starting unit on the bottom, ending unit on the top. This is the one we want. So we're going to multiply our starting volume by this unit. Now, here's where it gets tricky. Because we're doing a volume, you might think, oh, we need to multiply that 3 times. But here's the trick. Milliliters is a cubic volume, so when we make this adjustment, we only have to do it once. It just has to do with the way liters are defined, this relationship between liters and milliliters. We don't have to use that, the cube. We don't have to use it 3 times. And here's the cue to remember this. When you see milliliters, even though this is defining a volume, there's no power up here of 2 or 3. There's an invisible 1. So that's a cue to you to remember you only have to use the one adjuster. So this becomes 14,000 over 1,000. We're going to cancel that in just a minute. Notice our units cancel to give us the liters that we want. And we can just cross those off and we'll find out that our answer is that 14,000 milliliters converts to simply 14 liters. That's our answer. Boom. That's pretty easy, isn't it? 79.3 is a little bit, or 79.2, I'm going to let you guys do. No, that's not true. I'm going to do 79.2. We're going to make it just a tiny, tiny bit harder. This time what we're going to do is we're going to use unit multipliers to convert 4 cubic feet, so 4 feet cubed, to liters. Okay? I'm way over on the side of the paper. Hope you can see that. There you go. Okay? So we're changing our cubic feet to liters. So now what we're going to have to do is go, this is how we're going to plan the conversion. We're going to go from feet cubed to inches cubed to centimeters cubed, and then this will take us directly to liters. We don't have to, we know that the relationship between centimeters cubed and liters, we've got it right there. So we will use that one this time. I'm going to slide my paper up. Let's see, I want to keep that so we can still see what we're planning to do. Okay? So, let's take a look at our different units that we want to use for each of these conversions. For feet, we know we want to go from feet to inches, so we know that there's 12 inches in every 1 foot, and there's 1 foot for every 12 inches. So those are the two we'll be choosing from for our first conversion. To go to inches to centimeters, we know that there's 1 inch in every 2.54 centimeters and 2.54 centimeters in every 1 inch. So there are our choices for the second one. So that gets us to here, and we know that there are 1,000 centimeters cubed in every 1 liter, and there's 1 liter for every 1,000 centimeters cubed. All right? So there are our 3 sets of ratios. We will choose one from each pair, based on how our problem needs to work. So let's start with our 4 feet cubed, and then we want to choose the ratio that has our starting unit on the bottom. So that would be this one. So then we'll multiply it by 12 inches over 1 foot. Now notice we do have a cubed here, so we have to do it 3 times. 12 inches over 1 foot times 12 inches over 1 foot So now we've taken care of the first transition. Now we want to move, we've got things in inches, so let me move those. And we want to move that to centimeters, so we're going to use this version because it's got our inches on the bottom. That's where we want to go. So now we have 2.54 centimeters over 1. Oh boy, this is going to be a tight one, isn't it? Times 2 I'm going to just leave my units out. I'll write these in so we can cancel them. Okay? And that takes us to, so there, now all of our inches cancel out against each other. And now we've got centimeters cubed up here. I'm going to write them in so we'll have a place to cross them out. Now notice, here comes the fancy part. We want to use this one because it's got centimeters cubed on the bottom. But look, we only have to use it once, because this cubed cancels out all 3 of those. Oh, Ranger's got something to say about that. So that's the tricky part in this. Even though we have been using 3 of these, when we switch over and use our liters and cubic centimeters adjuster, we've got the cube built right in. So our final answer is 4 times 12 times 12 times 12. We're just gathering all these up. Times 2.54 times 2.54 times 2.54. Oh my gosh, so much writing. Divided by 1,000. Let's just cancel that out because we canceled those 3. And that final answer is liters. Woo! Long and intense, but not too hard. The tricky part in this is just understanding how to use these special ratios that we have defined in this lesson. All right, I'm going to have you guys go ahead and work example 79.3. And again, that is on page 328. And again, just use your notes. Make sure you have this information handy so that you can make the adjustments among those. Go ahead and do that, and then I will meet you back here for part B as soon as you're done. Okay, I'm going to cross off our first box because we did cover our metric volumes. And now I want to just say a few words about 45, 45, 90-degree triangles. That is part B of our lesson. And I'll start it down here in my notes. Now, we talked about the fact that 30, 60, 90 triangles always have a special relationship. And if we draw them like this, we know that the 60-degree angle is always going to be down here. The 30-degree angle is always going to be up here. And the relationship of the sides, this is how I remember. I always draw them the same way. 1, 2, square root of 3. You got your 1, 2, 3, you've got a square root. 2's the hypotenuse, always. If you memorize this, then any time you're trying to figure the lengths of the sides of a 30, 60, 90 triangle, remember that's the 90, you don't even have to use cosine and tangent and all that kind of business. You can just jump right to these ratios and do a quick adjustment. There's a similar relationship with (45, 45, 90-degree triangles. They're just as useful to memorize, and this one's very nifty too. It's 1, 1, square root of 2. Okay? So if you memorize these 2 triangles, it will make certain kind of problems super easy. I'm going to scooch up my paper. I'm going to keep that handy. You can still see those. And we'll look at example 79.4. I'm on page 329. And it says, use similar triangles to find x and y. So let me draw a picture. And mine's not quite perfect, but they tell us right here it's a 45-degree angle there. Well, if that's 45 and that's 90, then we know this has to be 45, 45, 90, and we know that we're using this style. Yeah, I think you can still see that in my work. We're going to be using these ratios. So it tells us the hypotenuse is 7. One side is x and the other side is y. All right? So the first thing that we're going to do is we're going to find the relationship between the 2 sides. We know that the ratios, the scale factor. They do this with a scale factor, and so that's fine. We'll do that too. Square root of 2 times our scale factor, and it will be going from this triangle to this one. So this, I'm going to just note, this is our left and this is our right triangle. So as we go from left to right, whoops, the square root of 2 side multiplied by some scale factor will give us 7. So just by doing a simple, that's not a point 2, that's just where I pointed. Those cancel. Our scale factor is 7 over the square root of 2. Whoa, our mathematicians' brains are going off because we've got a square root in our denominator, which we all hate. We don't like that. We want to rationalize our denominator, so we'll multiply it by square root of 2 over square root of 2. And so our scale factor adjusted is 7 times the square root of 2. I'm going off my paper, aren't I? 7 times the square root of 2 over 2. That number, that magical number, is what we will use to relate x to the original triangle and y to the original triangle. And what's super easy about this is that now we take the number on the left-hand triangle, 1, that's the length of this side, we multiply it by our same scale factor, and that will equal, for this one, that will equal x. Notice how they're matching sides on the triangle. Okay, so that's pretty simple to solve, isn't it? We know that x equals 7 times the square root of 2 over 2. And because 45, 45, 90 triangles always have legs that are the same size, and we've got that verified right here where we see the matching ones, we know that y is going to have the very same length. All right? So those are our final answers. That's example 79.4. There it is. I wrote that down. And that's all there is to it, you guys. That's how easy these are. You just use the matching sides to create a scale factor and use your knowledge of these similar triangles to solve other triangles that are the very same size. So dive into that homework and see how it goes. Good luck.